Hello. So please tell the friend to join. Hello. Good evening, everybody. So So this is the second class of regression analysis. We know linear regression depend on some assumptions. One, that is linearity. This means the relationship between x and the mean of y is linear. Secondly, equal variance or homoscedasticity that means the variance of the residuals that means variance of the residual is same for any value I fix. Third assumption is normality. Normality assumptions means residuals obtained from the normal distributions, and fourth is independence. That is, observations are independent. This can be done by Darwin-Watson test. We will discuss it later. So these are the four assumptions, and these four assumptions, these first three assumptions can be verified from the residuals plot. Here we consider the standardized residual. That means this is the residual. Suppose EI is a residual divided by root over variance of EI is a standardized residual, and we plot predicted means y hat. This is a predicted value of y. This is equal to a plus bx, predicted value of y corresponding x. A is a estimate of intercept term, or b is the estimate of slope. So we plot predicted versus standardized residual, and we see if following things are happening. That means there are pretty symmetric distributions. That means I will see that there are pretty symmetrically distributed, tending to cluster. This is cluster. Tending to cluster towards the middle of the plot. And also you observe that they are clustered around the lower single digits of the y-axis, that is, for example, 0.5 or 1.5, and also we observe that they are not any clear patterns. So if these things are happening, then assumption of linearity, assumption of equal variance, and assumption of linearity and assumption of equal variance or homoscedasticity hold. So from these residual plots we can check assumption of linearity and assumption of equal variance or homoscedasticity hold or not. If residual plot look like, then that means there are no there is no clear pattern. They are pretty symmetric distributed, tending to cluster around middle of the plot. See there. So middle of the plot, and they are clustered around lower single limit this value or this value. So sorry, this is not in this portion. So lower single value means this y-axis, this value. See that maximum data point lies between minus 0.5 to 0.5. So around, you can say that around 0.0. And similarly here also 0. Most of the data lies 0. Similarly here we also see that maximum data point lies within this interval. So this thing is whole. They are clustered around lower single digit y-axis, that is 0.5 or 1.5. Then we can say that assumption of linearity and assumption of equal variance or homoscedasticity hold. Okay. So tell me, can I go to the next slide? Please tell me if, can I go to the next slide? Are you hearing me? If so, then please tell me, can I go to the next slide and finish this thing? Can you hear me? Please tell me, can I go to the next slide? Please mention in the comment section. I am waiting. Okay, Devarati, thank you. So here we consider another residual plot. Here we see that if you look at the structure of the residual, then you observe that this type of pattern, maximum data point cluster around here also. You also observe this pattern and this pattern. Okay. So this plot are not evenly distributed. Vertically or they have an outlier or they have a clear shape. They have a clear shape. If you can detect from this figure, can detect a clear picture clear pattern, I think clear pattern. Clear pattern or print in your, for example, for this type of if this type of graph occurs in your module, has room for improvement. So if you look like this pattern or this pattern or this pattern, there is a clear pattern. You see that the maximum data lies in on the line y equal to 0, and if this type of pattern happens, or this parabolic pattern, or maximum point cluster in that way. So if this thing is happening, so there is a improvement. So we need to improve this model. Okay. So if the pattern is look like or this, then assumption of homoscedasticity violated. So this plot exhibit heteroscedasticity. So this plot exhibit heteroscedasticity. meaning that the residuals get larger as, see that, as x increases, value of y increases. That means residual get larger as the predictions moves from small to large, or from large to small. So if you observe in your residual plot, this type of pattern in your residual plot, you observe this type of pattern. That means the homoscedasticity does not hold. And suppose, for example, imagine that on cold days, the amount of revenue actually Anirban, I do not talking about taste. I just explained the residual plot. From residual plot we can verify whether assumptions of heteroscedasticity and assumption of linearity, whether assumption of homoscedasticity or assumptions of linearity hold or not. Okay, so just observing the residual plot, we can easily say that whether your model is suffering from heteroscedasticity or assumption of linearity does not hold. Okay, so this is the so actually I concentrate on only residual plot, not the taste. Okay, clear? Okay. So for example, imagine that cold days, the amount of revenue is very consistent. So Anirban, no problem. Imagine that on cold days the amount of revenue is very consistent, but on hotter days sometimes revenue is very high. And sometimes it is very low. In that situation, heteroscedasticity may occur. Okay. Sometimes often heteroscedasticity indicates that A variable is missing. So the problem is how to fix. That means if heteroscedasticity occurs, how to fix this problem. So next point is how to fix. The most frequently successful solution is to transform a variable. So just transform your variable, then you can fix this problem if heteroscedasticity occurred. So can I go to the next slide, Subhrojit? Shashwat, Devaroti, please tell me, can I go to the next slide? Anirban? Can I go to the next slide? Yes, Chundrima. Thank you. So, sometimes patterns like this means, like this example, if this shape or this shape, so sometimes pattern like this indicates that a variable needs to be transformed, because if this pattern is occurred, so assumptions of linearity does not hold. Okay, so in that situation we need to transform the variable, and maybe it is possible that the issue is a missing variable. Okay. So if this type of pattern occurred, then this means the assumption of linearity does not hold, or maybe there is some missing values in that situation. We need to transform the variable. Okay. That means transformation is needed. Yes, maybe log transformation, not only log transformation, there are so many transformation on it. Maybe you can use y if your y is uh, response variable, you can depending on the not only this type of graph, maybe another type of graph, depending on the situation, you may use root over root over y, log y, etc. There are so many transformations. Okay, so not only the log transformation, there are so many transformations you can use. And these transformation depend if the and you consider those transformation, just see just draw your scatter plot, and if your scatter plot look like linear, then you consider those transformation. But there are other methods we will discuss, that is move distance, etc. We will discuss later how to choose best transformation. Okay. Yes, log transformation, one kind of transformation. You're absolutely right. So, please tell me, can I go to the next slide if you finish this portion? So, if this type of things occur, that means there is a outlier, clear indication of outlier. So, if this thing is happening, we fix this. We fix this problem. Using actually, if this thing is if it happen, it is possible that there is a measurement or data entry error where the outlier is just wrong, in which can you should delete it. It's possible that what appears to be just a couple couple of outliers, just a two out, just a couple of outliers is in fact a power distribution consider transforming the variable if one of your variable has an asymmetric distribution like this graph. So actually I mean to say, if your residual plots look like this, means there is a clear indication of an outlier or outliers, presence of outliers or outlier. In that situation, if you the solution, not only the solution, just omit the outlier. If sometime the outlier may be legitimate, in that case you should assess the impact of the outlier. So in that case, the solution is you just transform the variable. Okay. So the last line is, if it is indeed a legitimate outlier, you should assess the impact of our outlier. Now this is a normal probability plot of residuals. So from this normal probability plot, we can judge whether the assumptions of normality holds or not. So from this normality plot, probability plot, we can judge whether the assumptions of normality holds or not. Okay. So a normality plot means, a normal probability plot means of the residuals is a scatter plot with the theoretical percentile or quantile of the normal distribution on the x-axis and the sample percentile of the residuals on the y-axis. The diagonal line, this diagonal line, which passes through the lower and the upper quantile of theoretical distribution, lower and upper quartile of the theoretical distribution Yes, we can also say this kind of plot is QQ plot. Yes, I am talking about QQ plot or normal probability plot. You are absolutely right. This is also another name of this is also called QQ plot. Thank you, Anirban. This normality plot we can also call this QQ plot. Okay, QQ plot or normal probability plot, which passes through the lower and upper quartiles of the theoretical distributions provides a visual aid to help assess whether the relationship between the theoretical and sample percentile is linear. If these points are close to the reference line or diagonal line, then we can say that the assumptions of normality holds. Otherwise, these assumptions does not hold. Okay. So note that the relationship between the theoretical percentile and sample percentile is approximately linear. Therefore, the normal probability plot, or QQ plot of the residuals suggest that the error terms are indeed normally distributed. So, can I go to the next slide? Subhrojit, Oyon, if anyone there, please tell me. Devarati, Tondrima, so, okay, so here we observe that the normal probability plot of residual is approximately linear. So these dotted points are sample quantile. So we see that the sample quantile very close to the these points, because these points are close to this straight line. This means sample quantile are also close to the theoretical quantile. Hence, we can say that the error terms are normally distributed. So, if your normal probability plot or QQ plot looks like, then you can say that the assumption of normality holds. Now consider, if you observe that your normal probability plot look like, and one observation is very far from this line, this means there is a outlier. This is the indications of outlier. And the corresponding histogram, if you draw the histogram, it also look like this. Okay. So please take your time to finish this. If it is finished, please tell me, and then I go to the next. Then I will go to the next slide. Okay. So this is the indications of an outlier. You can also check from normal probability plot of residuals whether there is an outlier present or not. So, can I go to the next slide? Yes, you can remove outlier, but thing is that sometimes the outlier may be influential or has some impact. So this is not always. This is not a good practice to remove outlier always. Okay. So in that situation, you need to transform the variable. I already mentioned this thing in my previous slide. So if the pure residual is look like, in that situation we need to transform it. I mentioned this thing. Okay. It is not always good practice to remove outlier. If you remove outlier, if this outlier is legitimate, then you have lost some. You lost some information. So in that situation, you consider the outlier and use transformation. Are you hearing me? If you satisfied, then please tell me, and I go to the. Okay, thank you. So this thing is finished or not? If it is finished, then tell me. Okay. So again we observe that if your normal probability plot look like this means this is highly skewed, and not this is also positively skewed. And if the pattern is, if it is an upward pattern, if the pattern is downward, it means this. If pattern look like this, in that situation you can tell your from the normality plot is that the distribution is negatively skewed. Okay, and for this example, corresponding histogram look like this. So we see that from histogram also, this is a positively skewed distribution. And if the pattern is downward, that means it is a negatively skewed distribution. So from normal probability plot, we can say that whether the distribution is symmetric or positively skewed or negatively skewed. So please tell me, can I go to the next slide? Chundrima, Ayum, please tell me, can I go to the next slide? Subrojit, can I go to the next slide? Okay. So this is the program. I consider income data. I already talking about income data. This is the data set. Okay. This is income. First column is income. Second column is happiness. So this is the R program. If you use this code to or Excel file, you need to save your Excel file in .csv format. Okay, either use this comment, these two comment for R, or you can use directly this comment. For this comment, for to this comment, we need to choose file from your source, and if you use this comment, you just write the path of your file. Okay. So this is LM for linear regression. Okay. So if you use this comment COF within bracket n, this gives coefficient of this linear regression, that is coefficient means your intercept term and slope. So if you look at the output, so you see that coefficient in gives you intercept term and income. Income means this is the slope, estimate of the slope or regression coefficient. So now you already knew this comment, summary of n. This gives these portions. I already explained this in my previous class. Okay, and this gives the residuals. This comment gives the residuals. That means y minus y hat. And for prediction, suppose you want to predict happiness when income is 6.1. Suppose I choose 6.1, which is I will be the sample range of income. So in that case, you first use this comment data.frame income equal to 6.1. Then if you use this comment predict n comma mu, then you get this value. This gives the predicted value of happiness when your income is 6.1. Okay, and this is the comment for the confidence interval of expectation of y given x, mean of happiness when your income is 6.1. So if you want, this gives your 90% confidence interval. If you want 99%, just change this value 0.9 to 0.99. Okay, this gives 99% interval. Another things, and in that case, your 90% confidence interval is this. This is the lower limit. This is the upper limit, and this is the fitted value. This also gives you the fitted value. Okay, and this comment give you 90% prediction interval of future observation when your income is 6.1. Okay, so again you can find different level of confidence interval, prediction interval for different confidence level, that is 0.99, 0.95, etc. Just change this level. Okay, and this gives plot n comma 1 gives the residual versus fitted plot. So this is the residual versus fitted plot, and here we observe that there is no pattern. Points are almost randomly distributed. That means assumptions of linearity and assumptions of equal variance hold. And so this is the residual versus fitted plot, and this gives the normal QQ plot or probability plot, normal probability plot n comma 2. So from this we see that the all points very close to the reference line. So this means assumptions are normality hold. So if you want to plot, if you want to plot these two diagram in a single graph paper, then you need to use this comment part image flow within bracket C2 comma 1. If you use this comment, this means your whole graph paper divided into two parts. This is first row, into two rows, okay, two parts, and look like, and then just write this comment plot n comma 1, plot n comma 2, then you get this, okay. And if you use, instead of this, if you use this comment part mf flow c1 comma 2, and then write plot n comma 1, plot n comma 2, then you divide your whole graph paper into two parts, then plot 1 here and plot 2 here, okay. So in that way you can paste your two graphs in a same graph paper. You not only pasted two graph papers, two plots, you can paste more than two, just changing this. Two plots means you have it, you in that case you divide your whole graph paper into four parts, and in that situation you can paste maximum 4 graphs here, okay. So in that way you can paste multiple number of graphs in a single graph paper, okay. So please tell me, have you any question? If you finish this slide, can I go to the next? This is the output portion. Okay. So please tell me, up to that, have you any queries or questions? I will explain it. Yes, of course. Here I do not consider such thing. We will definitely consider this later. Or you can find example. First you plot, draw the scatter diagram. If this thing is not look like linear, in that situation you try the different type of transformation. Root of that is root over a y log transformation, semi-logarithmic transformation, etc. But one thing, this is you can use R help you. Otherwise, manually it is very laborious job. Okay. Actually, we will discuss this later, okay? But for time being, you can try this thing. Take examples and try to feed this data. Maybe always first you draw the scatter plot. If scatter, okay. So just take an example. There are so many examples in internet. You can easily get this thing, and then you try yourself. And we will definitely discuss later. Okay, ma'am. So, any questions regarding the up to that part? Please tell me. Chandrima, Suprajit, or if you have a more question, please tell me. Devaroti, if anyone is there, please tell me if you have any question. Have you any question? Okay, Shubhrajit. Thank you. So next topic is multiple linear regression. Let y denote the dependent or study variable that is linear that is linearly related to k independent or explanatory variables x1, x2, xk through the parameters beta 1, beta 2, beta k, and we write y equal to x1 beta 1, x2 beta 2, xk beta k plus epsilon. This is called as the multiple linear regression model. Parameters beta 1, beta 2, beta k are the regression coefficient associated with x1, x2, xk respectively, and epsilon is the random error. and the mirror component reflecting the difference between the observed and fitted linear relation. Consider an example. The income and education of a person are related. It is expected that on an average higher level of education provides higher income. So a simple linear regression model can be expressed as income plus beta naught beta 1 education plus epsilon, which is error. Note that beta 1 reflects the change is income with respect to per unit change is education, say per unit change in education and cannot reflect the income when education is 0. As it expected that it is expected that even an illiterate person can also have some income. And this is the example where beta naught has real or practical meaning. Okay. Further, this model neglects that most of neglects that most people have higher income when they are older than when they are younger. Regardless of education. So this age also influential variable in that case. Age also another explanatory variable in that case. So in that situation, the model is income beta naught beta 1 education plus beta 2 age plus epsilon. Here beta 1 can be interpreted as this is the reflection of the change in income, reflection the change in income with respect to per unit change in education. Just write this thing, keeping after that keeping age is keeping age fixed, okay, or age kept fixed. You write beta here, beta 1 interpreted as the change in income with respect to per unit change in education, when age is kept fixed. Similarly, we can interpret beta 2 as a change in income with respect to per unit change in age when education is kept fixed. So in that way we can interpret beta 1, we can interpret beta 1 and beta 2. So in this case the model is matrix notation. We can write the model is write the model 1 as y curl, which is the observational vector x beta curl. X is a coefficient matrix, beta curl is a vector of parameters, and this is a vector of error component epsilon curl. Okay. Here we assume that this is the assumption. One, expectation of epsilon curl equal to 0, curl, assumptions to dispersions of epsilon curl, this is equal to sigma square I, and that means the constant variance and errors are uncorrelated. Assumption 3, x is a non-stochastic matrix, and assumption 4, this is epsilon follow in dimensional normal distribution with mean vector 0 curl and dispersion matrix sigma square I. Okay, these are the 4 assumptions. And we know the normal equations. I write here the normal equation. In that case, the normal equation is x prime x beta curl hat x prime y curl. So this is the normal equation. Okay. We take values. If beta curve hat is any estimator of beta curve for the model, not necessarily this is a least square estimator, it may be maximum likelihood estimator, moment estimator, etc. Okay. For the model, y curve x beta curve plus epsilon curve, then the fitted values are defined as y hat x beta curl hat, where beta curl hat is any estimator of beta, and if beta curl hat is least square estimator of beta curl, then beta curl hat is equal to x prime x inverse x prime y curl. And in that situation, y curl hat, which is equal to x beta curl hat, this is equal to x prime x inverse x prime y curl, then this matrix is called hat matrix. So at h equal to x prime x inverse x prime, and this is called a hat matrix, and it has which is, and this matrix is symmetric, secondly idempotent, that is, you can see that h square equal to h here, so it is the idempotent matrix. And thirdly, rank of h equal to trace of h, and this is equal to, k, not r, this is k. Okay. And another term is residuals. Residual curve, which is equal to y minus y hat curve, This is equal to I minus h y curl, and I denote this by h bar, where h bar is I minus h. And again also note that this h bar is symmetric h bar is idempotent matrix and rank of h bar equal to trace of h bar, which is equal to n minus k. And this is your homework. Please check that here also, if you define here the sum of square due to residual is nothing but a, so this is your homework, this, and then find expectation of SS due to residual, which is again n minus k sigma square, and MAC due to residual, this is equal to MS due to residual, this is equal to sigma square, which is the unbiased estimator of sigma square. And then this check that variance of y curl hat, which is equal to sigma square h. Okay, next homework, beta curl hat, which is a least square estimate of beta curl, is a consistent estimator of beta, and SS square, I think I think MS due to residual is also consistent estimator of sigma square. Please do it yourself. Page 3. Standardized regression coefficient. Usually, it is difficult to compare the regression coefficient because the magnitude of beta j curl, beta j, magnitude of beta j hat reflects the units of measurement of the jth explanatory variable xj. For example, in the following fitted regression model, y hat I plus x1 plus 100 x2, y is measured in liter, x1 is measured in liter, x2 is in milliliter. Although beta 2 hat very large than beta 1 hat, because beta 2 hat is 100 and beta 1 hat is 1, but the effect of both explanatory variable is identical. That means 1 liter change in either x1 and x2 when other variable is held fixed. Produces the same change in y hat. Sometime it is helpful to work with scaled explanatory variable and study variable. That produces dimensionless regression coefficient are called as standardized regression coefficient. There are two methods for standardized regression coefficient. Here I discuss one, that is unit normal scaling because this is the most common method. So define zij which is equal to xij minus xi bar. This is the z score corresponding xij, where Sj is a sample standard deviation, sample variance. Sorry, sample Sj square is a sample variance, and corresponding jth explanatory variable, sample variance corresponding jth explanatory variable so this is the sample standard deviation corresponding jth explanatory variable. Sample variance means we divide n minus 1 instead of n. Okay. So the formula is and y star this is equal to yi minus y bar divided by sy. Sy is a sample standard deviation corresponding study variable y. So in that situation your model reduces to yi star gamma 1 gamma j j sum over j from 1 to k plus epsilon I from 1 to n, because we use n observation. And in that situation, intercept term is removed. Okay. And here also the least square estimate of gamma hat, which is gamma hat, and this is equal to the least square estimate of gamma, which is equal to z prime z inverse z prime y star. Okay. So this scaling has, since this scaling has a similarity to standardizing a normal random variable, that is z score, so it is called as a unit normal scaling. Next point is coefficient of determination, which we define for simple linear regression in previous class. Which is simply the square of a simple correlation between x and y, And here the coefficient of determination R square given by capital R square, which is a square of a multiple regression coefficient, multiple correlation coefficient, and adjusted R square. So here we introduce new term adjusted R square, but simple linear regression we do not use this thing adjusted R square. When we introduce multiple linear regressions, so we need adjusted R square. We not only observe a coefficient of determination for goodness of fit, we also consider adjusted R square for multiple regressions. Let R be the multiple correlation coefficient between y and x1, x2, xk, the square of multiple correlation coefficient R square is called as coefficient of determination. The value of R square commonly describes that however the sample regression line fits to the observed data. This is also treated as a measure of goodness of fit of the module assuming that the intercept term is present in the model, then the model is yi beta 1 beta 2 xi2 beta k xik plus epsilon I from 1 to n. Then R square is nothing but 1 minus E curl prime E curl, where E curl is a residual y curl minus y curl hat sum over I from 1 to n yi minus y bar whole square. So this is simply as this gives sum of square due to residuals, and this is SST sum of square due to total, and this is nothing but a sum of square due to regression by sum of square due to total sum of square. Okay, so R square measure the explanatory power of the model which in turns reflects the goodness of fit of the model. It reflects the model adequacy in the sense that how much is the explanatory power of the explanatory variable. Here also note that R square lies between 0 to R square, 0 to 1 is chain, and R square equal to 0 indicates the poorest fit of the model, and R square equal to 1 indicates the best fit of the model. So if R square tending to 1, this indicates the best fit of the model. That means the value of R square very close to 1. This means the best fit of the model, and R square very close to 0. This means it's the poorest fit of the model. So suppose your R square is 0.95. This means this indicates 90% of variation, 90% or 95% of variation, 95% of variation in Y is explained by regression equation. And 95% is close to 100%. This means the fitting is good. It implies the fitting is good. In that way, we can expand R square. So, hence, this R square indicates the adequacy of the fitted model. Adequacy of the fitted model. So adjusted R square if more explanatory variable are indicated are added to the model, then R square increases. In case of the variables, in case if the more explanatory variables are added to the model, then R square increases. In case the variable are irrelevant, then R square will still increase. And gives an overall optimistic picture. With the purpose of corrections in overall optimistic picture, adjusted R square is used, and it is defined as adjusted R square is defined as one minus this is equal to where this n minus k and n minus 1 are degrees of freedom associated with the distribution of SS due to residual and SS due to total. Note that please wait, I think there is a problem. Okay. So note that our adjusted R square may be negative. For example, if you take k number of explanatory variables is 3, that is if you use 3 explanatory variables and 10 observations, then suppose your R square is 0.16, in that case adjusted R square, if you compute using this formula, then your adjusted R square is minus 0.25, which means, which has no interpretation. Note 2, if constant term is absent in the module, that is intercept term is absent in the module, then R square cannot be defined. In such case, R square is negative. So please check this thing. This is your another homework. Okay. So similarly, we can find prediction interval, confidence interval in that case. So here the confidence interval for expectation y given x naught curve, x naught curve is a given value of x curve is, you know this thing, I think you knew all this thing, so I just mentioned. This is a MSC, sigma x square is nothing but MSC, mean sum of square due to error or residuals. So this is a confidence interval of expectation of y given x naught when x is equal to x naught. And prediction interval for future observation. This is y naught hat p alpha by 2 n minus k root over sigma hat square 1 plus x naught curve x prime x inverse x naught curve comma y naught hat plus t alpha by 2 n minus k root over sigma hat square 1 plus x naught curve prime x bar x prime x inverse x naught curve. So this is a prediction interval. So you can use okay, Oyon, Mohammed Bilal, I am telling you, yes, I have a video, but I also teach this thing. I will teach this thing in my in coming classes. Okay, please follow this. Okay. So, Oyon, you asked me. Yes, in this example, you see that the adjusted R square is negative. It may be negative. Sometimes you get some values for which our adjusted R square is negative. In that situation, we cannot interpret this adjusted R square. So there is a possibility adjusted R square may be negative. Okay. So Mohammed Bilal, please follow our classes, consequent classes, coming classes. So you will discuss non-linear regression. Okay, or you can go our channel, you can find some video for nonlinear regression. Okay, thank you. So here you can use our comment ln y. Suppose if you use 3 explanatory variable, in that case you use this comment, and use same comment which I discuss. This is the comment. You can use this comment. You can easily find coefficients, that is beta naught, beta 1, beta 2, beta 3, or whatever the number of explanatory variables, depending on your number of explanatory variables. Use this comment summary m confident. Using this comment you can easily find the confidence interval of the coefficient. This is the, you can use the residual using this comment, and using this comment in that case you need to store in data dot frame. If your x1 is, give the x1 value. Suppose if you use 3 explanatory variables, suppose 3 explanatory variables, x1, x2, x3, then you want to predict x1 equal to some value. I think I take x1 star, then x2 star, and then x3 star. You want to predict y for the value x1 star, x2 star, x3 star. Then you first form data dot frame. We store it in this new. This is x1 equal to x1 star, x2 equal to x2 star, x3 equal to x3 star, and use this comment predict m comma new. You can get y hat. Similarly, if you use this comment, you can get confidence interval, and if you use this comment, you can get prediction interval. And use this comment for residual plot, and for this comment for normality plot or probability plot, normal probability plot. Okay, so same comment used for multiple regressions, and instead of this you use ln y curve x1 plus x2 x3, whatever your x. Here I use 3 explanatory variables, then you write x1 plus x2 plus x3. If you use 2 explanatory variables, then use x1 plus x2, and so on. Okay, and suppose if you store your data in data, so you write this common data. Okay, this is the comment. So similarly you can interpret this thing. So now your homework is, this is the homework. You should submit all this homework the coming Sunday. Okay, before coming Sunday. So the homework is, first you take a data set with at least 3 explanatory variables, and n should be greater than 30, that is the number of observations. Then use this comment, you find, you fit the model, and then find residual plots, probability plot, all these things, and interpret all these values, and also interpret all these plots and values, etc. Okay, so this is the homework, and you also complete the other homework, and you submit this homework before coming Sunday. So we will meet again on Sunday. Okay, at 6 p.m. same time. So yeah, have you any question? Please tell me. I will explain. Have you any question? So have you any question? I want to, before ending the stream, please tell me, have you any question or doubt? I will tell you, no problem. Okay. Devaruti said, no sir, please tell me, Ayun, have you any doubt? Okay, Shubhajit, Ayun, Mohammad Bilal, please tell me if you have any doubt. I will explain you. Yes, you can use non-parametric normality test, but here I also restrict our discussion on the this residual plots and QQ plots. Yes, you can use other non-parametric tests. There are so many non-parametric states. Okay, and you can use R code also for normality test. You can easily get this thing. Okay, you can also normality test. Using R. Okay. Have you any problem? Please tell me. Chungrima. Okay. Ayun, have you any problem? Please tell me. I think actually I like this thing. So please tell me, have you any problem? So, Ayun, are you hearing me? Swastik. Okay. So are you enjoying the class, Swastik? Okay, thank you. Swastik, are you enjoying the class? So I want to end the stream now. So thank you everybody. Thank you. Thank you, Swastik. So we'll meet again on Sunday at 6 p.m. So please till then stay with us. Thank you.